Hey everyone, and welcome back to my channel. Today we're going to do more of a practical sort of programming video about k-nearest neighbors, and it's going to be in Python. So this is something that has been requested in a sense to start doing more videos about my research and my work. So I think this is a good place to start because, as I mentioned in my last sort of machine learning video, I work a lot with case-based reasoning, and that means, understanding that similar problems have similar solutions. But if you want to check out that video, I'll have it linked for you down below where I described what case-based reasoning is. But k-nearest neighbors is a great way to implement case-based reasoning because the simple underlying factor of it is we expect that data points that are similar in input should be similar in output. So I've got a whole Python notebook here just going through the very basics of the way to implement this using scikit-learn. Not going through the entire algorithm from scratch because we don't need to reinvent the wheel here. We just want to understand how to employ it and how it works. So hopefully you enjoyed this video. If you do, be sure to give it a thumbs up because that really helps my channel out. And thank you so much to everyone who has been contributing to my channel by liking or commenting or subscribing. So really hope you enjoyed this video. Let's get into the code. Okay, so what is a kNN? So kNN is the k-nearest neighbors algorithm, and it's a supervised learning algorithm. And if you don't know what that means, I have a video where I explain the difference between supervised, unsupervised, semi-supervised, self-supervised, all of the different supervisions in machine learning. So if you want to see that video, I will have it linked for you down below. But just in very basic terms, supervised means that we have data that has some sort of label. So we have the question part of the data being the input variables, and then we have the output. So for example, one of the data sets you're going to see is a housing price data set, and they have different features of, number of bedrooms, the square footage of the house, all of that stuff. And then they have the housing price as the label. So basically, supervised means we have a labeled data, and we can do classification problems or regression problems. So a classification problem would be suitable for when we have data that the output is discrete. So for example, the output is yes or no. So like we might have data about patients with a different risk factors. So they're a smoker, they're older in age, and then the output will be, did they develop lung cancer, yes or no? So we're trying to learn whether they did develop lung cancer in future based on their risks. What would be the probability that they do develop lung cancer? So we're trying to learn that yes or no. Well, that's a discrete label. And for those situations, we want to use a classification algorithm. Then for regression, that's something we do if we have real number output. So on a scale. So like for the housing price data, that's obviously can be anywhere from 0 to millions, but it's done in dollars and cents. It's not individual numbers. It's not done in every 10,000. It's every single number in between 0 and several million, I guess. So that's the kind of situation where we want to use a regression because we have to learn, it's not learning a specific value in terms of 10,000 or 20,000, it's anywhere in between those. So that's what we do for regression problems. If you want to see a video with more detail on these kinds of things, let me know in the comments below. If you're very new to this stuff, you might not be following along, so just let me know. But basically, kNN is a way to solve various problems by taking into account the similar neighbors. So the way it really works is similar to my video on case-based reasoning. The idea is that similar problems have similar solutions. So having data that has similar input variables, we should expect to have a similar output variable between those two data points. So that's the basic idea behind k-nearest neighbors. And when you're implementing that in Python, the main library that you use for a lot of different machine learning is sklearn, meaning scikit-learn. So you can see here I'm using scikit-learn.neighbors and I'm importing nearest neighbors, k-neighbors classifier and k-neighbors regressor. I'm not actually using nearest neighbors in this. I'm just going to be using the classifier and the regressor. But essentially what the neighbours one does is, instead of doing the classification or the regression, what it does is it actually just returns the neighbours, the actual closest individuals to that one point. The way kNN works is that we set a number of neighbours, and this could be, for example, 10. That's the main example I use in this practical, just as a starting point. So basically then, for every single point in the data set, you want to get the 10 other data points that are as similar to this one data point as possible. So the closest ones by some sort of distance metric. And typically that's things like Euclidean or Manhattan distance. So it's like they have the vectors of all the data points, and you want to turn all of the input variables into one long vector, and then you're going to compare that vector with the point of interest. So for each point in the data set, we take its vector, compare it to all the other ones, and select the top 10 that are the most similar. So once we have our 10 nearest neighbors, then we can use their output variable as a way to estimate point of interest's output variable. You average those 10 points in some way. So if it's a classification task, you might do something like majority voting, where let's say 7 out of the 10 nearest neighbors says the answer is 1 and 3 say 0, then you take the 7 as the majority rule and that's the answer. Whereas in regression, because you're going to have all of these points that are very different, so $10,000, $12,000, all of those different kind of points, you might average that by using the mean or the median or something like that. And then that can be done either with no weights, so all of the 10 nearest neighbours, no matter how close or how far they are to the original point, they all get the same weight. Or what you can do is you can weight them based on the distance to the point. So those are the kind of options there. So now let's actually get into an example, now that I've sort of explained how it basically works. The key idea being that you expect that the points nearest to a point, if they have the similar input variable, they should have the similar output variable, and we want to calculate that. So the first example we're going to do is a classification task. So the data set that we're looking at is the iris data set. So it's basically classifying irises as different types. They have a ton of different features to do with the sepal length and all of these strange flower things that I don't really know anything about. But anyways, we're going to load that, and you can see this is how it looks. We've got 4 variables, and they have all of these continuous variables for the input data. And then this is the output. So this is the classification 0, 1, 2. I'm not actually sure what they specifically mean, but that's not really the point. Basically, it means that we can classify these flowers as 0, 1, or 2. And there is some meaning to what each of them is. But that's the first thing we want to do. So we can't simply use a k-nearest neighbours on this the way it is, because we need to have some form of machine learning in there. It needs to learn how to classify these flowers. The first thing we need to consider is how to split up the data. So how to make sure that we don't underfit or overfit. Underfitting essentially happens when our model has not been able to learn the underlying features, the underlying things that cause the difference in the data. It hasn't been able to learn enough, it doesn't have enough data to learn what actually causes the output variable to be a given value. Usually this happens when we just don't have enough data or we haven't found the correct model. Overfitting, on the other hand, occurs when we have fit the data too well. So it doesn't work well then on unseen data. So it works perfectly for the data we have a really high accuracy, but then when we have new data, it doesn't work anymore. So that's overfitting. So the solution to overfitting is to use some form of validation. So typically you would split your data in some way into a training set and a testing set. You fit your model on the training set, and then you test your model on the testing set to see if it actually is overfitting. So you might have really high accuracy on your training data and then have a lower accuracy on your testing data. And that would indicate that there's some overfitting going on. Another thing you can do is actually split it up into 3 different data sets. So you might have a training data set, a validation data set, and a test data set. So the training data set you would use to train initially. Then the validation set you use to actually just kind of tinker around with the model a bit to see if you can improve it, adjusting the parameters parameters a little bit. And then the testing data is used strictly for testing. Basically with the validation set, what will happen is if you change the variables a little bit, if you change the weights, the parameters, then if you do that and it changes the error in both the training and the validation set, then you know that it's something you should do. Whereas if it only changes the accuracy in the training set, then it's likely causing overfitting. So that's another option. More advanced is to use cross-validation. So there are a couple different types of cross-validation. I'm just going to talk about two. So leave one out, cross-validation, is basically where you use all of the data except for one point, and you use that one point as the testing. And the model is trained on all of the other data. But then you do this for every single point in the data set will have its own go at being the testing data point. And then you will average over all of those. Now, obviously, when you have a lot of data, this is very, very computationally exhausting and things like that. So that's not really done too often, but k-fold cross-validation is a more usable version of that, where instead we split the data into k-folds, and usually this is 5 or 10 folds. And then for each fold, we keep that fold as the testing fold, and then we use the rest of it as training. And then you repeat that for each fold, so each fold has a chance of being the testing fold, and then you average over all of those. So we're going to use that today, so you'll have a chance to see how that works in k-nearest neighbours. The next thing we need to do is then import cross-validation predict, because that will allow us to use the k-nearest neighbours classifier as well as having the cross-validation in there as well. So the first thing I'm doing is saying that my x is going to be iris data, and my y is going to be the target. Then my kNN is my k-nearest neighbours classifier, and I'm just setting nearest neighbours as 10 to begin with, and then we'll see can we improve that a bit. So then I'm doing predicting using my k-nearest neighbours, using x and y, and using a cross-validation of 5, so 5 folds. And then once we run this, you can see this is our predicted array, and you can see it doesn't look terribly different from the one we had before. Even just visually, it looks pretty similar. So that's a good place to start. And then to see, in terms of evaluation, seeing what are the accuracies, what's the error. So the two things we're going to look at today are mean squared error, which is the average of the squared error of the difference between the actual and the predicted values. So taking the actual vector, which is this one here, and the predicted one, which is this one here, then kind of taking the difference between those, so minusing those two from each other, minusing one from the other, squaring that, and then taking the square, then taking the average, and then taking the square root of that. Well, usually you would take the square root after that, so we're not going to take the square root today. We're just going to leave it as mean squared error, but often people would use root mean squared error, which is just the square root. So I need to import those from the scikit-learn metrics package, and that's what I'm doing. And then I'm going to calculate the, sorry, I should explain as well, the R2 score is the correlation between the dependent and the independent variables. So for the mean squared error, we want lower values, but for the R2, because it's the correlation, we want the correlation between the dependent and independent variables to be high, because that means that the dependent variables then explained all of our variance in the y variable. So we want that to be high. So I'm just going to print the mean squared error of y and y predicted and the R2 score. So you can see the mean squared error is extremely low. That's not something you would really find in practice. These data sets are what we call toy data sets, which basically means they've been made up for the purpose of learning how to do these things. So it's not super reliable. But then we have an R2 score of 0.97, which is really good. So high in this case means a value of 1 is the maximum you can get for R2. So 0.97 is pretty good. And for mean squared error, a value of 0.02 is something you will never get. It's so low. But anyways, I'm just going to use this as a good example for how the classification works. But then if we're trying to figure out in a different sense, what would be the best value for K? what you would typically do is run this algorithm over a number of different k's. So that's what I'm doing in this next section. So I have an array here for error, and then I have a for loop. So for k in range 1 to 51, we're going to make our classifier with the nearest neighbors now set to k, and then we're going to predict using that version. So that's all the same as it was before. As you can see here, that's all the same here. It's just that instead we're using nearest neighbors equals k, and we do that over all of them. And then at the end, we add on to our array the mean squared error so that we can see how that's changing for different values of k. So that's what I'm doing next, and that is super fast. When you have a ton of data in the real world, it will take a lot longer to run something like that. But anyways, so now I am using matplotlib.pyplot. So that is a way to graph things in Python so that you can have a visual representation of what's going on. So importing that, and then I'm just plotting our error versus our range that we were doing, so 1 to 50. So you can see here, like the error goes from 0.02 as high as 0.09, which is teensy error. You will really not get that in practice. So here we basically could have picked any value of k and it would have been pretty much the same, but 10 is the lowest it seems. So that was a pretty good guess to start. Okay, so that's a classification example, and it's not the best example in terms of the data set. So now we're going to do a more difficult data set and a more difficult problem. So we're using now the Boston housing data. So we're importing that the same way we did before. So sklearn.datasets load Boston data. So we're loading in that data, and you can see how this data looks. It's very continuous numeric, and the target is also continuous numeric. So we're going to be using a regression algorithm for this. So similar to before, I'm actually starting off the exact same way. So X is the Boston data, and then Y is the target. Then I have my kNN, but this time I have k neighbors regressor, and the nearest neighbors is 10 again, just to start off. And then doing the exact same thing as before, crossval predict kNN x y cv equals 5. So that's our cross-validation folds equals to 5. Again, super fast, wouldn't get that in practice really. Well, not necessarily, it depends on the data a lot. So we can't even really tell, is this in any way similar to what we had before? So that's the real difference between regressors and classifiers. Usually you can kind of see the difference, especially when it's ordered. So now let's look at the error. So here the mean squared error is 74, which, considering if we even just square root that, let's just see what it is. So let's just calculate that. Okay, so on average then we're off by about 8, and like looking at the values, they're somewhere between 14 to 20 something, seems between around 15 to 30, let's say. So being off by 8 on average is quite a lot. And you can see that R squared is 0.12 compared to before we had 0.97. So right now you can see we are way off, and that's good because it means we actually get to do something a bit interesting. So the first thing we're going to do is just see, like, maybe if we change the value of k, would that fix things? So same thing I was doing before, no difference here, except for again we're using regressor and we have k here. So I've run that, and you can see actually 10 was the best case scenario. So that's not a great start. Like if we go down much further, it kind of goes down again, but it doesn't really seem like 50 doesn't really seem like a reasonable number considering there's not a huge amount of data. So 10 seems like probably a better one to choose. So the next thing we can try to do to fix this is employ some sort of scaling. So because of the way the data is, which one's the data? So like it's on, all of the variables kind of differ a lot in terms of their min and max. So we want to scale the different columns so that the values are between, it depends on the kind of data, but between -1 and 1, let's say, so that they are in some way related to the min and max of the columns. It just depends on what kind of scaling you choose, but it basically just means you won't have any crazy large or crazy small values. So employing some sort of scaling is a good thing to do for this kind of data. It generally tends to fix some of the issues. So in order to do that, we need to kind of change up how we are doing our classifier. So first thing I'm going to do is import the pre-processing standard scaler. And that will just help us to scale the data. And as well, I'm importing from scikit-learn a make pipeline. So the pipeline I can make then is basically when you're putting in something into an algorithm, it means it'll just do the pre-processing and everything in one step. And then that was what it'll be using instead of what we were doing before. So here we're just making a pipeline for going into the predictor. So we're making a pipeline with standard scaler, so that's the scaling we're using, and then k-neighbors regressor equal to 10, with neighbors equal to 10. So that's our pipeline. And here you can see, instead of what I was doing before, which was cross-val predict with the kNN here, instead I'm doing classifier pipeline. So that means that we have, instead now we have the standard scaler and the regressor all in that one step. And now let's just see how that impacts things. So now we have a value that is much lower for our mean squared error. So again, if we just square root that just to see what that is like compared to what we had before. So 5.5 pretty much. So that's a good bit lower than before. And our R squared is now 0.64, which is significantly higher. So that's already a good first step to be taking. And yeah, so that's good. And again, let's just check, does anything change with the number of k? Not so much. Okay, so basically now we still have a lot of work to do. So the next couple of steps we can take, if we're trying to really compare models, you need to make sure when you're doing cross-validation that you are always comparing with the same data. So when you're splitting it into 5 splits, usually there is some sort of random process there. So it's important to make sure that you are using the same 5 splits each time. So that's just something we can add into our previous classifier pipeline. So here we're going to add in the k-fold. So this is what's going to split the data into k-folds. And then we're going to make our own cross-validation. So here we're splitting it up into 5 folds as before. We have random state is 0 and shuffle equals false. You can have that as shuffle equals true if you want it to be shuffled. But it basically just means if we're using this the same way the whole time, it means that we can really compare our models because we're always using the same data. And that's pretty important because otherwise a different split could end up having very different effects for the accuracy. So we want to just make sure, doing all of this again, just the same as before, we want to make sure this is the same as what we had before. Yeah, so that's what we need to do if we're comparing models. So from now we want to try to extend this more and improve it a lot more. And that will be done with some more slightly traditional machine learning techniques, which include feature selection. So what that means is the features are all of the input variables. And sometimes there's elements of the input variables, some of them are not actually useful for determining the output variable, and they actually make the accuracy worse. Or it could be the case that there's some underlying relationships, so there's covariance between variables, there's correlation between variables that is impacting the accuracy, and including an interaction term could be helpful. As well, it could be that there's actually a polynomial relationship, so maybe there's a relationship where one variable is related to the output variable in a squared kind of fashion. So that's a ton of different things we can do with feature selection. And as well, another thing we want to do when we're evaluating is not only to look at the mean squared error and the R squared, but also to look at our residuals. So that's like the difference between our actual and predicted, looking at the distribution of these and seeing is everything okay. Because sometimes we can get caught up in just trying to improve the mean squared error and the R squared. But if we're not looking at the residuals, it means there could be some serious issues in our model. So that I'm going to leave for our next video, which will be about feature selection. And and possibly evaluation. I'm not sure if I'll do those in the same video, but I just don't want to overload this one video. I basically just wanted to have it to be a good introduction to kNN. So I really hope that you enjoyed this video. I hope it was helpful. I hope you learned something in some way if you're new to kNNs, and I hope I was able to explain that well for you. If you did enjoy this video and you want to see any of the other videos I was talking about, be sure to subscribe and hit the notification bell so that you know when that video is uploaded. That is it for this video, and thank you so much for watching, and I will see you in the next video.